Sometimes it's useful for us to think about sine and cosine as functions of their angle x or their angle theta. And this is useful because the unit circle won't pass the vertical line test. It's not a function. But if instead we stretch it out, we let the x-axis be all of the angle measurements in radians, then we can think of sine and cosine as functions and analyze them the way we've been analyzing functions all along. So when we do this, we call the resulting function a sinusoid. So what I want you to notice is how I've labeled my x and y axes here. You're going to be expected to be able to create this on your own from memory without using your calculator. So just to remind you, here on the x-axis, I have 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, and so on. I can label my x-axis using that counting method I did on the unit circle, and then I can just reduce all of those fractions to their normal radian measure. Then the way that I'm plotting points is I'm using the unit circle values to plot the sine x or the sine values. And so when I do that, I know from my unit circle that sine of pi over 6 is 1/2, sine of pi over 3 is radical 3 over 2, sine of pi over 2 is 1, and so on. And if I plot all those points from the unit circle, I get one period of the sine wave. And what's kind of interesting about being able to plot this sine wave is it gives us an alternate way to remember the sine and cosine values of our basic reference angles. So for example, if I wanted to know which angles had a sine of 1/2, I could just go ahead and draw a horizontal line from 1/2 and see where it intersects my sine graph. So I know the sine of pi over 6 and the sine of 5 pi over 6 is 1/2. This is kind of a cool alternate way to labeling your unit circle, because you could do the same for positive rad 3 over 2. So you would know that the sine of pi over 3 and 2 pi over 3 have the same value. You could do it for negative 1/2, and you would know that the sine of 7 pi over 6 and 11 pi over 6 is negative 1/2. And you could also do it for negative square root of 3 over 2, and you would know the sine of 4 pi over 3 and the sine of 5 pi over 3. We can also analyze this function. Even though we've only graphed one period, this function repeats. It's periodic, and so the domain is all real numbers, even though we only see one period here from 0 to 2 pi. This function is bounded below by -1 and above by 1, so its range is -1 to 1. The symmetry of sine is odd. The end behavior is not defined. If we were to go out on the x-axis towards infinity, there's no way to tell where the sine function would be. We do know it would be somewhere between -1 and 1, but since we can't pinpoint that end behavior exactly, we can't define it. This function has a behavior called oscillation. It oscillates between -1 and 1 indefinitely and forever. The period is the amount of time on the x-axis it takes the sine curve to complete one full rotation, so one full rotation up and down to come back to its starting point as a period of 2 pi. And the amplitude is the height. So on this graph, the height is 1. This is a parent function. You should know this by heart. You should be able to graph it by hand accurately using the unit circle. The other parent you should know is cosine x. Here's the graph of cosine x. Again, notice I labeled my x-axis to be the angles going around the unit circle. And then I used the cosine values of each angle to plot the points to create a similar curve for cosine x. Cosine x has the same domain, -infinity to infinity. Its range is also bounded by the same values. However, it has even symmetry. There's no end behavior for the same reason as sine. It has the same period. It takes 2 pi to complete one wave, and it has the same height and amplitude of 1. So once you know these parent functions, you can use transformations and move them around and change the shape of the graph, just like we did for the other functions in this course. So to do that, we're going to talk about how to do transformations. And on the next page of your handout here, you have sinusoids and their transformations. So this should all be a review. Hopefully you know how to find these things. But if we have a sinusoid, which is either a sine or a cosine, that has some transformations worked on it, then that's going to change the shape. So this coefficient A here, an absolute value, is the amplitude or height of the curve from the center line to the top. The period, or the length of time it completes one full wave, can be computed by taking 2 pi and dividing it by the absolute value of this guy here, B. You're going to have to add these absolute values in on your sheet. They weren't originally typed there. The frequency is the number of complete waves it completes in a specified interval, and so we would take just the reciprocal of the period and divide B by 2 pi. D, any number that's added or subtracted to the end of sine or cosine is the vertical translation. And C divided by B, we have to keep in mind that this B may be here, will give us the horizontal translation. So I had wanted to show you guys these graphs in Desmos, but I'll go ahead and use my graphing calculator the best way I can to kind of show you what happens when we do some transformations to these functions. So to start, I'm going to take a look at the parent cosine in my graphing calculator. Sorry, let me kind of clear some of these out. And let's just look at cosine. So there's our cosine, our parent function. Now what will happen to cosine if I do 1/2 cosine x? Well, that means that the a value is 1/2, so our amplitude is 1/2, which means we should expect the same shape but a shorter height. So let's look at 1/2 cosine x. There he is. And you can see here that he is 1/2 as tall as cosine x. What will happen if we do -3 cosine x? Well, then a is -3. If I take the absolute value of that, I should expect the graph to be a little bit taller with a height of 3. And we're also going to see a negative there. So that's going to give us a reflection across the x-axis. So here's cosine, our parent. And now watch both a reflection and a stretch. So notice now that this reflected down and has a height of 3 in each direction. So the value in front of the function changes the height and possibly a reflection as well. Okay, let's look at what happens to this sine parent when I make some changes to that. So here's our parent sine, the one you should know. And we're going to see how changing the inside value affects it. So here, our b value is 1/3. So if I do the computation for the period, 2 over 1/3, multiply the top and bottom by 3, I should expect that it's actually going to take 6 pi in order for my graph to complete one full period. This is a horizontal stretch. So I'm actually going to go to my window here and change it. I'm going to make sure I'm in radian mode here. And I'm going to change my window to be -6 pi to 6 pi. And I'll have it count by, let's say, pi over 6. And let's see what happens now. There's sine x. I'm just going to change my window a little bit, bear with me. There's sine x. And this, of course, is 2 pi. So let's make that window a little bit bigger. Let's make it -6 pi to 6 pi. And then let's put on the stretch and see what happens. So there's regular sine, but now this is 6 pi, so we should expect 3 of them in there. And there is sine of x over 3. So remember, we changed this to be 6 pi. So now one curve takes 6 pi, or our parent has 3 in that amount of time. Let's see what happens now if I do sine of -2x. Well, over here my b is -2, which means my period is pi. So we'll end up with a horizontal shrink, but we'll also see a reflection across the y-axis, which is harder to see because of the symmetric properties. Let's go back and change our window back to -2 pi to 2 pi, our standard window. And let's leave sine x on. Let's just remind ourselves what he looks like. So now we're back to 2 pi, so one parent here. And if I do now sine of -2x, I should expect there to be a horizontal shrink. So now the period is only pi. It only took pi to complete one full wave, or 2 pi's in the original period. So changing the x value creates horizontal stretches and shrinks. So let's go back now and see what happens if we do more than one thing at a time. So we'll look at our parent cosine, but here we're going to expect a couple things to change. The amplitude is going to be 4, which will give us a stretch, And also the period's going to be pi, which will give us a horizontal shrink. So we're going to look at cosine just to remind ourselves what he looks like. There's cosine. And then let's see what happens if we do both the vertical stretch and the horizontal shrink. Whoa, yeah, so he's 4 tall, and he's only taking pi here to create 1 full wave. Or he creates 2 full periods in 2 pi. But he only needed pi to get 1 full wave done there. Okay, so now let's look and see what happens if we do 2 things to sine. So here, number 4, we've gone ahead and shrunk horizontally sine, so he's going to become shorter. He's also going to reflect because of that negative. And we should expect, again, a horizontal stretch. It's going to take him 4 pi to complete 1 rotation. So let's go back, take off cosine, put on sine, and just remind ourselves what the parent looks like. There's our parent sine. And now we're going to do 2 things to him as well. We're going to, 3 things technically. We're going to reflect, we're going to shrink, and we're going to stretch. So what I want you to notice here is that this positive portion is now negative, and it's much shorter. It only has a height of 1/3. And look at this full up, down, and back up takes a total distance of 4 pi, because remember we have 2 pi on this side and 2 pi on that side, so it's a stretch of 4 pi to get the complete wave. Okay, last but not least, we're going to look at a shift. And there's something interesting happening here at this shift. So let's do our parent sine again, and then we're going to look and see what happens if we do sine of x plus pi over 2. And what that's going to do is it's going to give us a shift left of pi over 2. Well, look at that. Looks a lot like cosine. It graphed our parent second that time. So sine and cosine are related. They are, in fact, the same sinusoid, just as a shift. By a factor of pi over 2, which is also kind of interesting. So in the next and final video, we'll go ahead and try and graph some on our own from scratch.